Hi everyone, thanks for watching the standing wave part 1 video. In this video I'm just going to go through what a standing wave is and some of the parts of a standing wave. I'll also talk about something that we call harmonic frequencies and harmonic series, and then finally we'll end up with doing some math associated with standing waves. So to begin the video, the first thing that I want to talk about is what is a standing wave. A standing wave is a very specific type of wave. It arises when an incoming wave and a reflected wave meet, and this only happens at certain frequencies. It actually causes the wave to appear to stand still, where certain points move a lot and certain points don't move at all. So what I'd like you to do right now is just take a moment and watch this brief video clip to watch a standing wave in action, and I'll label some parts for you, and then we'll come back and write some notes. So take a look at this video clip.
By swinging a rope back and forth, we can demonstrate the phenomenon of standing waves. When we swing it faster, at a certain frequency, the wave seems almost to stand still. This is a standing wave. When we increase the frequency even further, a different pattern develops.
So now that you got to see that video of a standing wave in motion, you probably saw that I put labels on there of the two key points of the standing wave. We have the node, which is a point that doesn't move, and the antinode, which is a point that does move. So what I'd like to do is put that down in some notes for you. So if I draw a standing wave, and there's many different types of standing waves, what I'm going to do is I'm going to draw one that looks like this, and I'm going to label 3 nodes. So this is what it looks like in one shape, and then I'll draw a dashed line to show what it would look like when it vibrates. It goes through a half a vibration. And these points right here are called nodes. And nodes are points of zero displacement. So there's a node right there, and a node right there. Capital N, node, node, node. So on this particular standing wave, there's 3 nodes. There's also 2 antinodes. Antinode here and an antinode there. So let's write antinode. And these are areas of maximum displacement. Those are the areas that seem to vibrate a great deal. And they just go up and down. Also associated with a standing wave is the distance from the 2 endpoints. How far apart are the 2 endpoints? How long is the string? We call this length L. And it's the length between the endpoints. Usually it's written as the length of the string. So these are the key points of the standing wave: the node, the antinode, and the length between the endpoints, sometimes commonly known as the length of the string. And there's a lot of different standing waves that occur. A typical one, a most common one, is like a guitar string. It's fixed at both ends, so there's a node at one end and a node at the top of the guitar, and in the middle it vibrates up and down when they play a note. And what ends up happening with standing waves that are kind of interesting is that there's a series of frequencies that all result in a standing wave, and we call this a harmonic series. And what I'd like you to do right now is take a look at a brief animation of different frequency standing waves that are all somewhat related to one another, and they occur within the same ending point. So take a look at this little animation on a harmonic series. What you're looking at right now are 3 standing waves that all form within the same length or distance between endpoints. The one on the top is called the fundamental frequency because it has the lowest frequency, and each one below it is just an integer multiple of the original standing wave, or the fundamental. The second harmonic is twice the frequency of the first, and the third harmonic is 3 times the frequency of the fundamental. And you can see as we go up the harmonic series, we get more nodes and antinodes. Okay, so hopefully you got to see the different harmonics in a harmonic series for standing waves, and what I want to do is just draw each of them right now. Here we have the first harmonic, also known as the fundamental frequency, and it's the lowest frequency that you could possibly have to create a standing wave. And standing waves don't always occur at every frequency, so this is the lowest possible one. And there's my third interruption, so I'm just going to keep going. Scott Christie should report to the main office. But for the first harmonic, there's going to be a node at each end and an antinode in the middle, which means that there's going to be a large vibration in the middle. And I like to draw a dashed line that represents where the antinode goes to. So there's the nodes at each end. And that's the lowest possible frequency that you could have. And the way that we mathematically represent the number of the harmonic is we use a lowercase n. So you just see n for number, and this is n equals 1. That's the lowest frequency that you could possibly have for a harmonic. The second harmonic is a little bit more complicated. All we do is add one node and one antinode. So I'm going to have a node at each end and one in the middle. And in between each node, just like the first one, is a half a wavelength. So this will be a half, and then a half there. And I like to draw the dashed line to show where it's going to vibrate to. And we have three nodes in this case, node, node, node. And then up here we have an antinode, and also an antinode. So there's two antinodes, and this is harmonic n equals 2. And for the third harmonic, again, we add another node. So there would be 4 nodes. So each time we're just going to add one more node and one more antinode. So this will vibrate up, and in between each node, set of nodes is a half a wavelength. This is going to vibrate down, up, node, 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 one more node, and 3 antinodes. And this is harmonic n equals 3. Now, what frequency determines a standing wave is very difficult to come up with right now. We have a set of equations that we'll learn in just a minute that will help us predict that. But let's just say, for example, that we find out that our fundamental frequency for the first harmonic is 10 hertz. We know that to create another standing wave within these endpoints, we must have an integer multiple of that. So for the second harmonic, frequency number 2 has to be 20 hertz. It's 2 times the original. And frequency number 3, frequency of the third harmonic, has to be 30 hertz. So what we find out is that the frequency of any harmonic number equals the harmonic number times the frequency of the first. And that's an equation that we can use to calculate the frequency of any harmonic in the series, as long as we know the fundamental frequency and the number of the harmonic. Now, the last thing that I want to show you is a little video on how we actually calculate the math associated with standing waves. So take a look at this, and then I'll come back and write a few more notes to finish this video lesson.
A standing wave with 2 fixed boundaries must have a node at each end. The first standing wave has 1 node at each end and an antinode in the middle. This is the first harmonic, corresponding to the fundamental frequency. Its wavelength is twice the length of the string. The second harmonic has another half wavelength. In the second harmonic, the wavelength is equal to the length of the string, and a node appears in the middle. Each new harmonic has an additional half wavelength. The third harmonic. The fourth harmonic. When a wave is fixed at both ends, wavelength is twice the length of the string divided by n, the number of the harmonic.
All right, so to recap what was said in the video, we have a way of calculating the wavelength of a standing wave, and the way that we do that is, let's first draw again the first harmonic.
Castro, please come to the front office. Allie Castro, please come to the front office.
Another interruption. We continue. So I'm going to draw the first harmonic of a standing wave, and this is a standing wave that's fixed at both ends. And teaser trailer, for for the next video lesson is that there's different types of standing waves. They don't have to be fixed at both ends. They can be free to move at both ends, or one end can be fixed and the other can be free. But we're just doing fixed at two ends for right now to get things started. And what happens in the first harmonic is that we have only one half of the wave. The other half of the wave kind of exists out here. It doesn't exist, but you could project it almost. And if you have half of the wave and you know the length between the ends, the wavelength is equal to 2 times that length. But this is not a complete equation that I've written on the right, because if I go to the second harmonic, which has 3 nodes, and I draw this wave in there. It's probably my best wave of the video. Well, the first one, not the dashed line. That was best. But if I look at this length, which is the same, this length, if I multiply this by 2, well, this is one complete wave. But I've multiplied that length by 2. Now I have 2 times the wavelength. So the way we adjust for this is we divide 2L in the equation by the harmonic number. So this would be 2 times the length, but then divided by 2. So this length equals the wavelength. And if this were the third harmonic, then we divide by 3, and the fifth harmonic divide by 5, and so on. So 2L divided by N is the way that we calculate the wavelength of a standing wave if we know the length and the harmonic number. Now, one other bit of math that we use a little bit, the first harmonic has 2 nodes and an antinode. And the second harmonic has 3 nodes and 2 antinodes. And if we wanted to figure out how many nodes are there, that equals the harmonic number plus 1. If you look at the first harmonic, it has 2 nodes, so the N number, N equals 1 for the first harmonic. 1 plus 1 gives me 2 nodes. The number of antinodes is equal to the harmonic number. So if we do our second harmonic, for example, the number of nodes should equal, if the second harmonic is 2, it should equal 2 plus 1, and there's 3 nodes. And if we have, let's see, how many antinodes would there be in the second harmonic? Well, there would just simply be 2. So I actually have a question on the next page. See if you can answer it. It says, a standing wave is created between 2 fixed ends. The wave occurs in the 6th harmonic. How many nodes are present for this wave? So take a second and see if you can figure that out, and then I'll do the answer. So the number of nodes equals N plus 1. So I can say, well, we're in the 6th harmonic, so N equals 6. And 6 plus 1, so the number of nodes equals 7. There's 7 nodes. And that would allow me to draw this. So there are some of the basics of standing wave. We have the basic terms, node and antinode. There's a harmonic series that occurs, and they're all integer multiples of one another once you find one of the standing waves. And then we have an equation to calculate the wavelength, which is just 2L divided by N. So you should go to the link right now and do the questions for the standing wave video, and make sure that if you have any questions, things that you don't understand, write a comment to me and I'll try to answer it in class. Thanks.